this particular model feeding 1,680 gallons a minute to this frac application, and we had a pump trip scenario. So we can zoom in. Again, this is the end of the line on our data and look at what happened from a pressure standpoint. Again, very low pressure as we're feeding the piping system. We're trying to maintain 15 psi. As you can see here, our steady state pressure is 25 psi. And when we had that pump trip 7 miles away, you see the pressure goes and drops, basically to cavitation, minus 14.7. And again, you're in a vacuum condition. That vacuum then oscillated, came up as a vacuum, oscillated back as a high pressure wave. And this again is ductile iron pipe in this 24-inch line. The fittings and seals for ductile iron pipe is usually, the pipe itself might be able to handle a full vacuum, but the seals itself can only handle, say, a -6 vacuum condition. So we're going to go in and solve that particular problem in the field. Again, zoom back out in the model. We can go into the pump station. Turn on the surge vessel, which will give energy to that pump trip. And see how the pressure will, again, we're trying to maintain a positive pressure in the line. We're dealing with very low pressure at this particular point. And remember, we're pumping up, down 7 miles. At the end of the line, our minimum operating pressure, as I said, was 25 psi. But again, we want to try to keep that positive. We want to keep the whole line positive, and we don't want this negative wave oscillating back and forth. Every time that negative wave would go out, our air vacuum valves would open up, which is introducing air into the system and air out of the system. This again, because it's a frac water application, we want a zero discharge through the air vacuum valve. So if we can keep the line positive and not relying on the air vacuum valves, we can minimize them leaking in the field. So again, I'll zoom back out and we'll look back at the end of our piping system so we can see the cause and effect. At this particular node, what's great about the software is that we can run the model, with the surge tank online, as you see here, or again, maintaining it right at 0 psi in the design. And we can look at what happens if we did not have the surge vessel. So again, this case, pressure vacuum, pressure vacuum, pressure vacuum, we're introducing a lot of air into the system. And again, this is reuse water, or this is, frac water, which can be, corrosive. So we want to minimize the amount of air that we're letting into the line. Also, the air, we're trying to minimize or reduce any air coming into, the frac skid, because we don't want to be introducing air down, 6,000 feet into the earth. And again, from the air vacuum standpoint, I'll click on the actual valve there, and we can say, in one case the valve is opening up. You can see at the bottom here, under that scenario, the valve would open up, and we can actually, in the software, look at that air valve and see the volume of air introduced into the line itself. As I say, both cases that valve is opening up. In one case, it's allowing a lot of air into the system. The other case, it's allowing a smaller amount of air into the system. So what's also interesting about the software is that we can look at the whole from the pump station to the end of the line. This will show us all the input data, the length of the pipe in the system, and then the hills and how the lay of the land lies. And that we can look at our steady state and our maximum pressure envelope in the system. Again, this is with the surge vessel. And you can also see at the end the 2 points at the end, one of which I did show you the air vacuum valve. that air is introduced at that point. Before, that transient wave was affecting the whole entire piping system, and the negative pressure wave would be allowing all those other air vacuum valves to open up and allow air into the piping. So you can see this is a well-balanced system, and at only 2 points at the end, we're allowing air to enter into the piping. Just as an example, I'm going to grab, let's just say, this air valve, and you can see what's happening, you know, midline. It's letting air in, whereas with the surge vessel and giving energy, we never allowed air to enter into the piping system. So this is bringing water into that control valve, into that skid, and again, we're modeling and looking at that flow rate through this control valve and maintaining a good constant flow and pressure. But understand that constant flow and pressure starts all the way at our reuse water or our river or lake, and to make sure that particular pump system is well balanced and designed so that we feed water properly into the system. So from that standpoint, we're supplying the water, all is well. What happens as we're transferring water between the two pumps? So again, here would be an example of, you know, a booster pump injection system, and just looking at what happens if the operator at the end closes this particular valve. And we're simulating a valve closure. In this case, worst case scenario, our change data would be someone walking up to that valve and kicking the valve closed in 2 seconds. And the phrase is, what do you mean kicking the valve closed in 2 seconds? Well, in this case, you're looking at an 8-inch butterfly valve with a lever handle on it. And what they do is they hook it with their boot and kick it closed. All right? And I see this in the field, I'm like, if I have my computer on there, I'm like, oh, thank you, because I just grabbed some beautiful data showing how you're going to have this huge up pressure surge. And you know, he closed the valve and he's like, wow, look at the piping up there moving as it's like snaking along as the shock wave goes through that piping system. So we're going to look at, again, from a computer modeling standpoint, we look at the worst case scenario, the what if. If someone can do it, that's what we're going to model it for. From a control valve standpoint, we've got some control valves we've got to close in less than a half a second. And these are, you know, 600-pound class trunnion mounted ball valves that I can close in half a second. So again, this case we're looking at operator in the field closing the valve in 2 second scenario. And then what happens, okay? We had an earlier discussion, do I put a pulsation dampener or surge vessel right at that frac skid? And then, you know, how do I, all this equipment, as you saw the trailer with the injection pump, this is all on you know, tractor trailers, 18-wheelers. We got to be able to move from location to location. So to take a surge vessel with you is kind of difficult, okay? So do I have a surge vessel, or can I get by with a safety relief valve to deal with this application to protect my piping system? But then I have to deal with the amount of water coming through this relief valve. So again, before we buy equipment and ship it all over the country, we simulate in the model to look at the worst case scenario. So let me run this scenario. I'm going to go ahead and turn off this surge vessel also. And the relief valve is closed. And here's our pumping data. And we're basically pumping, and we're going to see what happens when we turn off that valve. So we're operating at, you know, 150 psi at this point, and when we shut that valve, we hit 500 psi, and my piping is rated to 285 psi. So this is a huge problem, and again, who knows what's happening on the side of the, you know, the deep, you know, the injection point, but this is the shock wave that he created, or she, sorry, in closing that valve. So how do you deal with this shock wave? This, again, is unacceptable. We're flexible piping, and we've overpressurized our piping system. So one of our solutions would be, you know, what if we put in, a surge vessel to accept the energy as that valve closed. So I'm going to turn on the surge vessel, rerun the model, and look at the cause and effect. So we accept the energy, but the issue going on right here is that somebody did not turn off the booster pump. So what happens is we accepted that 500 psi pressure wave, which occurred when they closed the valve in the 2 seconds. So we have that upsurge that we accepted the energy, but then that wave oscillates down the piping system back towards our pump, and we drive the pump to dead head. Okay? With that pump still running, this is what we're simulating. So we can look at the cause and effect here. So we can minimize and accept some energy, but then we've got to do something with the pump. And we're simulating this out for 200 seconds. As you see, it's pretty, the wave's just oscillating back and forth. So we'll go back to the same node where we have our chemical injection skid. And we can look at the cause and effect with and without. So we've minimized that pressure wave, but we're still exceeding the pressure rating of our piping. So we still have a problem. Again, through simulation, we can look at, okay, let's try this, let's try that. Instead of going into the field and saying, hey, let's put this, $30,000 surge tank out there, I think that'll solve the problem. We can use computer engineering to size and look at the different scenarios. So in this case, well, that still didn't solve our problem. So let's go back into installing a pressure relief valve. So you have one of two options here. It's either if someone closes in that valve, we turn off the pump, okay? Or you put in a relief valve. So you can see based on the model running over the next 200 seconds is that the high pressure wave was accepted by the surge vessel. It oscillated back to the pump, the relief valve opened up, and then it closed, and then everything settled down because even with the pump running, that relief valve will be either open or we'd be at the left-hand side of the curve and start to heat up the pump. At that point, someone would turn off the pump. Let's see what the data looks like. With the relief valve in place, we keep the pressure below, 160 psi. We didn't overpressurize our piping system, and that's a great solution. Now you might be able to go back in the model and say, all right, how much water is actually coming out of that relief valve? Because at that point I have to look at the flow rate that we're dealing with and containing and dealing with that actual frac water. So you can see the valve opens up and stays open for 20 seconds to relieve that high pressure wave. And the software simulates the actual flow rate. So we can calculate how much water is coming out of that relief valve to deal with this problem. So again, as you start the process, in this case you need a couple extra empty frac tanks to accept that water from this surge event. And again, this would all be from a safety standpoint. This should never happen, but if it does happen, it's been contained. We didn't overpressurize our system. We didn't blow apart, a very expensive, chemical injection skid. And again, assessing the risk of our system in fracking our piping so that we don't have an overpressurized system. So again, different ways of dealing with the water as it's coming from, feeding that injection pump into the frac skid. So then, again, just some food for thought, what happens on the downstream side of that pump? So I call this Frack Earth. And it's dealing with high pressure injection pumps. So take a look at this particular pump. We're dealing with 17,500 feet ahead in an injection pump. And we look at the cause and effect of a pump trip here. So we can run the model first and foremost. Let me zoom all so you can see. To this point right here. And then from that node, we can simulate out and look at what would happen as we're building up the pressure in the shale and it breaking away. We can simulate that as a valve opening up and looking at the cause and effect of how the pump is then going to shoot off the curb because we don't have that head, and we can look at that wave oscillating back. In our reuse water class, we're going to address that and what happens when you have this sudden burst of energy as we break apart the shale. In this case, in the model, is what happens when we launch the pig through a piping system in a reuse water system. So again, there's lots of ways to simulate what happens. So let's look at strictly a pump trip down into the earth. So we've run the model and we're basically looking at the injection pump, which I'll grab on the model, and we're looking at data as we're fracking a well. In this pump, we have a pump trip, what actually happens in Mother Earth, okay? So if we look at our steady state, our pressure, we'll grab a node on the top side here and look at what we're looking at from a pressure standpoint. And again, the injection point, we're looking at a little over 9,000 PSI, okay? And as we're pumping down, when we had a pump trip, we see that pressure dropping down to 8,400 PSI. So it's like, 800 PSI pressure differential within a fraction of a second. And then so that wave oscillates down. And remember, our piping system might be, 3 miles down into the earth. And again, it's the same thing with our shock wave. That shock wave traveling 3,000 or 4,000 feet per second down into the earth and then oscillating back. So again, our time step, you'll see the negative wave going out, comes back, and then shoots back up to almost 9,600 PSI. So again, when we look at the piping design as we're doing this frac application and as we're building the pressure up, remember, we're building the pressure up till we shatter the shale, and then again from a chemical sand, we're trying to fill in that formation to lock it in. But that initial burst, what does that do to our pump? So we can simulate the pump running and then just experiencing this release of energy, which will create a similar shock wave into our piping system. And the point is to make sure I don't overpressurize my piping system itself. In this case, almost 9,600 PSI. So that's on the top side. Let's look at, in this case, down into the earth. In the shock wave pressure, 9,000 PSI, the shock wave differential, and you can see how that wave oscillates back and forth. Interesting part about, again, the software is I can look at the top side and the bottom at the same time. So I go into group mode in the model. I grab the top piping node, bottom piping mode, and I can compare the data at both points. So again, in this model and simulation, we're trying to control, the pressure and flow. In this case, in the model, we have our booster pumps feeding the injection pump. And again, if the injection pump trips, again, high pressure, low pressure piping interfacing with high pressure. Again, having a check valve there and that check valve closing rate. What happens when that valve slams shut? We're going to have an upsurge, and we can simulate it looking at, how does that pump trip in the high pressure piping affect my low pressure piping? Okay, so here's my shock wave that occurred in my low pressure piping. In this case, we're exceeding the pressure rating of that piping, getting up to 1600 psi. And again, this is what happened when the injection pump tripped. That shock wave is coming back into our piping. Again, this is a higher pressure scenario than what we were looking at before. But again, you can see how this could damage the piping in the equipment, in the injection equipment, if this shock wave is allowed to enter into our low pressure piping. So again, in this scenario, we see the worst case scenario is tripping the injection pump, and we look at ways of accepting energy. If you look in our model, and again, I have multiple pumps here. We look in our model, I've put in a solution to protect my low pressure piping. Let's see what happens. So grabbing a node and looking at accepting energy when that injection pump tripped. So with and without, you can see how drastic. Again, looking at the solution in the stress on the piping. And again, this huge difference in accepting and giving energy when that pump tripped. So hopefully in the last 30 minutes, if we edit that right, it gives you a better feel for, fracking, the frack water, the equipment you might have in the field, and wonder where it could be damaged, say in your chemical injection skid, and how. Would it be pump transients caused by either the pumps themselves, control valves, or human operator error? So we don't overpressurize the system, is to do a computer surge analysis of the system and then put in a transient monitoring computer so that if you do have a design error in your system, you can make corrections by evaluating that data.